Hello, Professor Simmons here. Going to talk to you today about projectile motion. So we're moving from one-dimensional kinematics, describing motion with math that we saw in Chapter 2, to talking about things moving in 2 or 3 dimensions. So, and this is fun because projectile motion opens up lots of different kinds of problems. So you can have uh, problems where, instead of just dropping an object like we have been doing, you could throw an object off of something, or you could throw an object up off of something, or you could throw it down and see what happens. There's really a wealth of problems. Or you could have situations where you throw something from the ground and you want to know, for example, how far it goes, or you want to know how high it goes. And it just really adds literally another dimension to this discussion of motion. And it may sound initially like it's kind of complicated, but it's really, it builds very logically on what you already know. So let me just give you strategy for approaching these problems. Here's the game plan. Remember we talked about vectors? Well, you need to break the situation into x and y. Okay. You use the y is really free fall. If you can do a problem of all the different kinds of free fall problems, you can solve for what's happening in the y direction during projectile motion. Generally, this gives us time. And then if you have the time, you can find the range. So if you have the time, directly this is going to tell you, for example, if if you've found the x velocity, then you can multiply by the time that you find from free fall, and then you know how far your object's going to go. Okay, so we can get more sophisticated about this. For example, let's talk about something called the range equation. Okay, and this is one simple scenario. So I'm going to be talking about the situation where you shoot something off the ground at some angle, and we'll talk about our coordinate system being y equals 0 being at the ground. And let's break this problem down algebraically and just try applying the strategy that I just described to you. So, and I should say here, this projectile has some initial velocity, v. And like we discussed, velocity is a vector. So let's look at the y direction. We need the component of that velocity that is in the y direction. And that's going to be the initial velocity times sine theta. Okay. Actually, I'll indicate this initial velocity as, how about v naught? Okay, so if we know the y, what do we do next? We can find the time. Okay, so remember this one-dimensional kinematics expression we used all the time in chapter 2, that y is going to be y naught plus v naught t plus 1/2 gt squared. Actually, I'll just write this as a for now, And then let's make a couple notes here. So if we're throwing and landing from the ground from y equals 0, both of these would be 0. And also recognize that if we are talking about acceleration due to gravity, that's going to be g, and it's also going to be pointed down. So this would become that. And then you can see we can solve this. So actually, and I should be careful, this is really v naught y, right? We can then solve this for the time. Or sorry, notice there's two solutions. There's one immediate solution. T equals 0 would cause both sides of this to be 0. And that would be, the instant before you throw it. So that's one solution. So let's divide out this factor, one factor of t. Okay. And then solve for the remaining t. Okay. And let me put this in, let me write it like this. How about just to be a little more neat? I'll substitute in what we know v naught y is. We can cancel out this negative sign, make this all a little bit more concise. We'd have that. So that's an expression for the time. So if we know the time, then what do? We can find the range. So we know. Now for the range, we need v naught in the x direction as well. Recognize that our v naught x would be v naught cosine theta. Okay. And then, so our range would be v naught x times time. We found the time up here, so we can substitute that in. So this would become, and we'll substitute in this as well, our v naught x. So we'd have this combination v naught cosine theta times 2 v naught sine theta over g. And you can see some of this would simplify a little bit. This would become 2 v naught squared sine theta cosine theta over g. So this is a function for the range. So let me write that. I'll write this as a function. This range depends on, what does it depend on? The initial velocity v naught and the angle. Okay. And actually, we can write this a little more concisely if we use a trig relationship. An identity here. That sine of 2 theta is equal to 2 sine theta cosine theta. So when we incorporate that trig identity, we get our most compact expression here. That the range is equal to, so making use of that, that trig identity, v naught squared over g times sine of 2 theta. Okay. Now, something that's kind of interesting about this is, so so this is the special case where you're going from the ground and landing on the ground. So if you were throwing it off of something, this wouldn't apply, in other words. So be careful about that. But notice, it's kind of interesting. The question that crops up with this is, well, like, what angle should you throw it at to get the largest range? And you could approach this with calculus, right? You could take a derivative of this with respect to theta and find where that would be equal to 0, and then that would tell you the maximum of this function. You could also look at this, and maybe you just see it. What's the maximum value that sine of an angle can have? Would be 1. And when is this thing going to be maximized? That'll happen when theta equals 45 degrees, because then when 45 times 2, you get 90 degrees. Sine of 90 would give you 1. So this thing is maximized when theta equals 45 degrees. So in other words, if you want to throw something the farthest horizontal distance, or launch something the farthest horizontal distance, you want to do that when theta equals 45 degrees. Let me just draw this cartoon bigger here. If you throw it at a smaller angle, it'll be short. If you throw it at a larger angle, it'll also be short. So 45 gives you the max range. Cool. So this is an expression that they have in your textbook, and we'll make use of it here with an example in a second. So that kind of shows you how I recommend thinking about this. You look at y, you find the time, and then you can find horizontal distance. So let's look at a few examples. So let me try and paste one in here for you. Okay, so this first example, we have a ball thrown horizontally from the roof of a building, 9 meters tall, and it lands 9.5 meters from the base, and we want to know what's the ball's initial speed. So let's make a picture here. We're gonna have this building that's 9 meters tall. We know that this thing is going to be thrown horizontally, some initial velocity. Let's give ourselves a coordinate system. We'll put y equals 0 at the ground, just sort of for convenience. And then we know this thing lands over here, 9.5 meters away. And we want to know the initial speed of the ball. So, okay, let's apply what we've been doing. So, if we look at y, we can get the time. So, what do we have going on in y? Notice, if we're throwing it horizontally, that's another way of saying that v naught in the y direction is 0. So this piece would be 0. We know what the initial height was. And we also know what the final height is going to be. That will also be 0 because we've set our coordinate system at the ground. So then we can solve this situation for the time. So let's do that. We'll pick up, so you'd have 2 y naught over g equals t squared. So we'll take a square root of this, and we'd have square root of 2y naught over g is going to give us the time. And so now we have an expression. So looking at that, now we have an expression for the time. And so what do we do next? If we know the time, we can find the range. Oops. What is going on? My pen here. Sorry. So find the range. So we know that x, v naught x times the time. So we can put the time in that we've just found. Now in this case, we know what the range is. So what we're solving for is the velocity. So the velocity is going to be the x divided by the time. So let's put everything in. We know that that x is going to be 9.5. We know that our time here, we'll put in all our numbers. 2 times 9, 9.8, square root. And notice we can check the units here. We'll get something that has units of meters over seconds, which is what we want because we're looking for a velocity. And if we crunch the numbers here, we would find that this would be 7 meters per second. And you might think you kind of skipped a step. I did kind of skip a step. In the framework that I gave you, this was like step 2, and this was step 3. And that was because we didn't really have to break this into x and y, because by saying it was thrown horizontally, that told us that the initial velocity in x, the initial velocity was in x and only in x. Okay, let's look at another example. So let's see here. So now we're talking about a shot putter. I'll make this a little bit bigger so it's easier to read. So we have a shot putter throws a shot, mass 7.3 kilograms, with an initial speed of 14.4 meters per second at an angle of 34 degrees to the horizontal. Calculate the horizontal distance traveled by the shot if it leaves the athlete's hand at a height of 2.1 meters above the ground. Okay, let's give ourselves a picture here. So here's the ground. We have a coordinate system. We're going to have the shot. So it's going to originate at some initial height of 2.1 meters. Try and draw this a little bit neater. Okay. And it has an initial velocity, 14.4 meters per second, and it's thrown at an angle of 34 degrees relative to the ground, to the horizontal. So let's give our strategy a shot here. So first, let's break into x and y. So, of course, the velocity in the x direction would be v naught cosine theta, and our velocity in the y direction would be v naught sine theta. Okay, because we're launched at an angle in this problem. And then the next thing is we want to find the time from y direction. So let's do that. Remember, y is going to be y naught plus like that. Now this problem is a little bit more complicated in this respect than what I showed you with the derivation of that range expression, because notice this is being launched from one height, but it's going to land on the ground. So while y, the final height, is going to be 0, the initial height is not. So the consequence of this is that, let me just rewrite this in descending order. Is that this is a quadratic. So in order to solve this, we would have to use a quadratic formula. You could plot this as well. Like I mentioned to you in the past, be careful with these quadratics. It's easy to make mistakes about things like signs that can get you turned around. So, but what you would do then is you would use this to find the time. And since it's quadratic, you'd have two solutions. Now, only one of those solutions is positive, and that's the one that you would want. You'd find it's about 1.85 seconds or something like that. So if we know the time, then we can do step 3 here, where if you know the time, we can find the range. Just combining the ingredients that we have from steps 1 and 2 here. Cosine theta times our time. Let me just write this out. Numbers here. You'd find that you get about 22 meters. So that's an example that's showing, the free fall aspect of this, the y part. Since you land at different heights, it gets, or you start and land at different heights, it adds a complication in that you have to solve that quadratic compared to the simple range equation. Let's look at one other quick example. Paste it in here for you. So in this example, it's kind of a silly question, but it's actually kind of a simple question. We have a grasshopper that's hopping down a level road. On each hop, the grasshopper launches itself at an angle of 45 degrees and achieves a range of 1 meter. What is the average horizontal speed of the grasshopper as it progresses down the road? And assume the time spent on the ground between hops is negligible. So part of the thinking with picking this question is that it gives us a chance to apply and reinforce this range expression that I mentioned for you. So recall that the range as a function of the initial speed and the angle looks like v naught squared over g times sine of 2 theta. Now notice we've picked our special angle of 45 degrees, so you put 45 degrees in there, you would get that this thing becomes 1. So in other words, this becomes v naught squared over g. And we actually know what the range is, this 1 meter. So we can solve this. Actually, let me call this r. We can solve this then for the initial speed. That would give us the square root of g times r. Okay. But, oh, and this is why you always want to draw a picture first. That velocity is at an angle of 45 degrees. And what they ask us for is the horizontal speed. So we want to know v naught x. So we've sort of done our strategy a little bit backwards. But now that we know what v naught is using the range expression, we would get the x part of that. And so we would need to multiply v naught by a factor of cosine theta. And so we would end up with root gr times cosine of 45 degrees. And in fact, this cosine 45 degrees, that's one of your special angles. You may have that memorized, that this is the same thing as root 2 over 2. So this comes down to root g r times square root of 2 over 2. And so we could notice that our r was 1. So we could write this as the square root of 2g over 2. Or we could just crunch the numbers and find that this is about 2.2 meters per second. So that gives you an example that employs that range expression. So hopefully these examples help you see how these projectile motion problems are really a very logical progression from what we've talked about in terms of motion in one dimension and free fall, as well as adding in vector decomposition.